Welcome to our meeting. Happy New Year. And Mick sends his regrets. He's a little bit under the weather right now, so you're stuck with your old meeting chair for the meeting tonight. So my name is Dave Chisholm, and I'm also the president of the local group here. So welcome to everybody. A special welcome to members from other RASC centers. So we are in a Zoom webinar. So the only people that can talk are those who are the panelists. But if you do have a question for anybody who's on the panel, please use the Q&A bottom at the bottom of the screen. We monitor that during presentations, and we will push the questions forward to the presenter. The chat box, just a reminder that your comments can be seen by all. And we will not be monitoring the chat box for questions. So if you have a question, please use the Q&A. Raise your hand is disabled. This is also being recorded. So I'm doing the introduction instead of Mick. Then I will be doing the Ottawa Skies for January. And we have members in the news and some other announcements prior to my presentation. We welcome Haley Sapers. Sorry about the spelling of your name there, Haley. We didn't quite catch that. And then Mark Lilienthal will be talking about polar alignment. We have some AstroTrivia over the break. Rick Wagner will talk to us about the RASC Robotic Telescope. We have a bunch of really neat observation reports, and we have our observation challenges and other announcements. So welcome to new members. We have 75 new members in 2022, and we've had new members join us just recently. So welcome aboard, folks, and please keep in touch with us. So members in the news, first one. So Andrea Gironis, she has received 2 certificates, the Astroimager Solar System Certificate. She got that on the 13th of December, and the Astroimager Wild Field Certificate, and she got that on the 24th of November. So congratulations, Andrea. Malcolm Laurel was in Sky News Photo of the Week, and he's actually online here tonight. I believe he has, yes, he's second in our observation reports. So this is the Crescent Soap Bubble Nebula, and I'm sure he can speak to that when it comes to his section. So congratulations there. And Abdur Anwar, the Embryo Nebula Photo of the Week as well.
Sorry, that's my mistake. That's supposed to be a slide of Oscar's Photo of the Week that was just announced in Sky News, and I've somehow grabbed the wrong slide. My apologies, Oscar. We'll get it in next time.
Okay.
I'll forgive you this time, Chris.
There you go. So, would you like, if you welcome to visitors who are with us, if you're not already a member, if you'd like to become a member of the Royal Astronomical Society of Canada, regular membership is $103 a year. Family membership is $97.50 plus $16.90 for an adult and $9.20 for a youth. So that's a better deal if you've got sort of a husband, wife, and kids who want to be involved. It's a better deal. And then for students or youth membership under the age of 25, if you're a student, the cost is $62.40. So what do you get from this membership? Well, you have access to the Ted Bean Telescope Loan Library. We have a bunch of telescopes that we can loan out. We once we get back into the Canadian Aviation and Space Museum, we'll have access to the Stan Mott Library. But if you are looking for books on astronomy, we do have some that we've extracted from the library, some beginners books. Please reach out to us and we can get those to you. We also have our private observatory, the Fred Lawson Observatory out near Almont. It's on the sort of the far side of the Milliken Tail, and members have access to that site. Through the national office, every 2 months you get the Sky News magazine. Every I think it's 2 months or 3 months, you get the RASC journal. That one is delivered electronically. The Observer's Handbook you get sort of in December of the year before. And monthly, we have our local newsletter called Astronauts. But the biggest benefit for being a member of the RASC is the people. These are just some of the members of the RASC that you'll get to know over the years. So, Andrea, hopefully your audio is working.
Hello, can you hear me?
Yeah, you're good.
Oh my gosh, sorry about that. I had some problem. So I think I'll maybe just click. I don't see any headings. No, I guess we're missing some. In any event, I just wanted to briefly speak to everybody about that I'm going to be the light pollution abatement volunteer for our center. And many of you who, of course, are interested in astronomy, we all know that how light pollution can affect our ability to enjoy our hobby. However, the impact of light pollution goes far beyond just our hobby. It impacts the environment, it affects animals, humans, and can also keep young people and future generations from enjoying the night sky. Our center has a long history of being involved in light pollution. One of our members, Robert Dick, is an internationally renowned expert and tireless advocate in this area. But if you are a regular Ottawa member like myself, you might think, well, what can I do? I'm just one person. And that's a good point because it is a big topic and it's not the kind of issue we can advocate on our own. We need to gather many people who have different skills, different connections. We need to have educators, communicators, technical people, and just basically anybody who really wants to advocate to save the dark skies, get involved. And what I'm hoping to do just to start is a call for volunteers for other members of our center. If you want to get involved, I'm hoping to put together a small group that we can meet, we can brainstorm. I have some ideas. I'd like to get feedback and hear other ideas. And hopefully, if you want to contact me directly, and on the website, you'll find an email assigned to light pollution abatement, lpa@rasc.ottawa.ca. If you have another email for me, I respond to all emails, whether it's work or personal, because they're all the same for me. So please send me an email, and I'd like to hear from all of you, and I'd like to mobilize a small group to sit down and discuss some of the priorities and short-term, long-term projects and things we can actually do to make a difference. So I hope to hear from you. Thank you.
Okay, thank you, Andrea. Ottawa skies, here we go. I'm just going to place a spotlight. There we go. So this will be an astronauts, but this is the planet visibility for 2023. So I've been sort of working through my slides. I've got my slides done up until June, and anyways, take a look at this. Gives you an idea sort of what are the best times to go out and see the major planets. Here is the moon phases. So tonight, this is a good time to have our meeting. It's a full moon. It's washing everything out. This moon was known by our Indigenous peoples as the wolf moon, because it's the time of year when the hungry wolf packs howled. This moon has also been known as the old moon and the moon after Yule. Our new moon is on the 22nd. This one I did put up last month, so you sort of missed it, but they're still up there. We have the Quantrids meteor showers. I think even if you did try to go see them on January 3rd and 4th, I'm pretty sure we were covered in clouds and rain and so on. In any case, this one, just hang on a second here. I just got to move my slides forward on my comments here. Oh, I don't have it. In any case, they are still visible for the next little while. So as you can see, the days are getting longer, finally. So here we go. There's the sunrise and set for the month. So Mercury, best time to see Mercury is on January the 30th. We call this the greatest western elongation. So you look for the planet low in the western sky just before sunrise. It'll be further separated from the sun. Venus is visible now in the evening. Mars is visible in the evening, and Mars is going to be visible for quite some time, next number of months. Jupiter's visible in the evening. Saturn is visible in the early evening. This will probably be the last month that we'll see Saturn for a while. Uranus is visible in the evening, as is Neptune. And this is our cartoon of the month. Thank you, folks. So I'm really excited to welcome back Dr. Haley Sapers. She last presented in March 2015. She received her PhD in planetary science from the University of Western Ontario in 2012, where she worked on trace fossils preserved in meteorite impact glasses and the biological significance of meteorite impact structures on early Earth and Mars. She's done a lot of work since she last visited with us, so we look forward to her presentation. So welcome, Dr. Sapers, and Chris is going to stop sharing and let you bring up your screen.
Wonderful. Thank you very much for the introduction, Dave. And thank you, Chris and Michael, for the invitation to speak here again. I'm just going to start sharing my screen here and get this hopefully working.
Looks good.
Wonderful, thank you. So I'm joining this virtual meeting tonight from Toronto, where I am an adjunct professor at York University. So I just wanted to begin by York University's land acknowledgement and to acknowledge the presence on the traditional territory of many Indigenous nations. The area known as Takaranto has been caretaken by the Abenaki Nation, the Haudenosaunee Confederacy, and the Huron-Wendat. It is now home to many First Nation, Inuit, and Métis communities, and we acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. This territory is subject of the Dish with One Spoon Wampum Belt Covenant, an agreement to peaceably share and care for the Great Lakes region. So today I wanted to talk a little bit about how we search for life if we don't really know what we're looking for. I mean, life is a very difficult concept to actually try to define and to pin down. So I'll talk a little bit about some of my work with the Sherlock team at NASA JPL. And Sherlock is one of the instruments that's on the Perseverance rover, currently in Jezero Crater on Mars, looking for signs of life. So before I get into some of that research and some of those updates, I'd like everybody to just take a moment, maybe close your eyes, and just imagine that you're sitting in a concert hall and you're waiting for that very first single fraction of a sound. Perhaps the director is standing there with her baton raised. The instruments are up at the mouths of all of the musicians. And just before the conductor lowers her baton, you hear the very first single fraction of a sound. And your brain would probably interpret that as music. That's what you're expecting. You're in a concert hall. That fits the context for where you are. But if you went out onto the street and you heard that exact same single smallest fraction of a sound, your brain would probably interpret it just as noise. And you'd also be correct. So how can we take two of the exact same signals and come to two completely different, but both correct conclusions? So what is the single smallest fraction of a sound you can hear before music exists? At what point when you hear a sound will your brain interpret that sound as music? Somewhere between silence and sound, we have music. And so I want you to just think for a minute, and I'm going to play a couple of sounds here, and maybe just use the chat box to chime in with anything about when you think this is music. So at some point, we arrive at music. And we have the same continuum for life. It's not a harsh line, but somewhere between non-living and alive is the idea of a biological system. We have things like viruses that are right on the edge, and they're not typically classified as non-living or alive, but they're certainly signs of life. And so we have this continuum, and it's very difficult to actually define what life is. And so if we can't define it, how do we know what we're looking for? And part of knowing what we're looking for is this idea of context. Are we expecting to find life? Are we expecting to find something that is alive? And so going back to that music analogy, when you're sitting in the concert hall, if you're listening for a sound and you hear a sound, your brain is probably right in its interpretation of music. But if you're not, if you're just out on the street, it's probably just noise. And so as astrobiologists, especially those of us that are searching for signs of life on other planets, we need to be able to kind of hone our tools and techniques and our information to make sure we can pick out that signal from the noise. So Earth is our concert hall. And when we step beyond Earth, we must be careful not to miss the noise, but also to make sure that we are searching in the right places to hear the music at all. As scientists, we like to take things apart. We like to put them into nice, neat boxes to explain them, to categorize them. But when we do that, we lose this notion of the whole. And so you can see these two sets of images, and the images on the left present a structure, the whole picture. So you have pine needles and you have sticks arranged in the pattern of a branch. And that pattern, that whole system, actually tells us a little bit about emergent function. Same with the stars in the sky. We get patterns, we get distances. When we take those components apart and categorize them and organize them, we might get more information about all of these parts of the whole, but we lose this idea of emergent function. We lose this emergent structure. And when we think about the concept of life, what's really important is capturing this system as a whole. And we'll go into that, why that's problematic in a couple of slides. But this is one of my favorite quotes. Chaos was the law of nature, and order was the dream of man. And sometimes I like to remind myself of this. But before we go into some of the problematic issues with trying to characterize life, what do you picture when I say life on Earth? Something like this probably comes to mind, lush rainforests and trees and animals and all of these, macroscopic life that we see all around us. And if I were to ask the question, where is all of the life on Earth? Is it on the surface or is it in the subsurface? You'd probably say, well, it's all around us. It's on the surface. And if we go by biomass alone, so the totality of all life, the mass of life, you'd be correct. Marine and terrestrial environments account for about 87% of all life, while the deep subsurface accounts for only about 13%. But what if we were actually to talk about numbers of organisms? So numbers of trees or numbers of animals or numbers of microbes. We actually have a dramatic shift. Up to 96% of all microorganisms on Earth are actually in the deep subsurface, about 8 meters below our feet. So if we're talking about the distribution of life on Earth, it's actually distributed into the subsurface. The subsurface habitability is about 2 billion cubic kilometers. That's twice the volume of all of the oceans. And the carbon mass of life in the deep subsurface is up to about 23 billion tons. And we found life to about 5 kilometers of depth in the continents, in the crust. And in marine water, it's about 10 kilometers from the ocean surface. So microbial life on Earth really is distributed in the subsurface. So when we think about what life looks like on Earth, this is probably a more accurate depiction if we think about life as a whole and by the numbers. So this life in the deep subsurface uses alternate sources of energy. It doesn't rely on energy from the sun at all. This life has really slow growth. We don't know a lot about it. Low biomass. We're discovering new organisms almost daily from these environments. But this life is all relatively new. It's only really in the past decade that this has been recognized, that there's actually life that can use carbon sources that aren't organic, or can use energy sources that don't rely on photosynthesis. And so I love this cartoon from Beatrice the biologist. And it's this idea is that, how can we even imagine life to exist in these environments? And so here we have life at the bottom of the ocean and hydrothermal vents going, do you think there's life at the surface? Like, no way, there's no hydrothermal vents at the surface. What would they possibly use for energy? And I like to flip this around. So the only life detection mission that we've sent to the surface of another planet was Viking. And Viking landed on the surface of Mars in 1976. It wasn't until 1977 that the very first hydrothermal vents were discovered on an oceanographic cruise off the coast of the Galapagos. And in fact, there were no biologists on board that cruise because at the time it was inconceivable that there could be life at the bottoms of the ocean. So the only life detection mission we have sent to the surface of another planet was actually designed and sent and data collected before we even knew what most of the life on Earth is actually capable of doing. So why is it so hard to figure that out? Why is it so hard to define life? And that's because the definition of itself is a bit of a quagmire. So none of these actually tell us what a definition of life should do. A definition of life should become a quintessence of the notion of life. Definitions should be technically precise and conducive to research, but accessible to the initiated in other areas and compatible with common sense. Definitions should be as simple as possible. We need a definition of life that more effectively and precisely captures the fundamental essence. None of these are actually helpful or useful in defining life or even trying to tell us a bit of a search strategy. So then we can define life by its characteristics, by breaking it apart and categorizing it. So energy, life is acquiring energy for growth, adaptation, and reproduction. Maybe it's reproduction and evolution. Maybe it's development and reproduction. All of these are problematic. Art has an evolutionary history. Fire takes in energy and grows. Minerals have self-replication, and each evolution of a mineral responds to its environment, changes a little bit, and provides a template for the next iteration of that mineral. So none of these descriptions, none are unique to life. I'll talk a little bit more why this is problematic as well for looking for life as we don't know it. So here we have life. Most of the life on Earth is in the subsurface. Most of that life is actually physically attached to rocks. What's really good about this is that any type of life interacts with its environment. And when life interacts with its environment, it leaves behind signatures of that interaction, or what I call biosignatures. And so biosignatures are these signs that can be found or detected that give us a clue that perhaps life was there. And so biosignatures can be really easy to identify. I mean, if you show this picture to pretty much any preschooler, they'd be able to tell you the difference between a bird's nest and a pile of sticks. And some biosignatures are like that, dinosaur bones, really detailed stromatolites with cellular textures intact, footprints. These are really unambiguous biosignatures. But over time, these signatures can get affected by the environment. They're subject to attrition. And sometimes life grows so slowly that they actually don't build up a biosignature that's really easy to identify. So we end up with something like this that's very difficult to identify and really difficult to actually ascribe uniquely to life. I just want to do a little bit of a thought experiment here. So I'm going to send everybody out on a mission, and I'm going to give you a list of ingredients. And this list of ingredients describes something in a grocery store. And so based on this list of ingredients, just write in the chat window what it is that I'm describing in the grocery store. So we have flour, sugar, eggs, and milk, and a zucchini. So this is a list of items or characteristics that describe one item that can be found in a grocery store. And so what is it here that I'm actually describing? I'll just give a minute or so. I can't actually see the chat box, so I'll just give a minute or so for people to put some ideas in there.
You got one suggestion, which is zucchini bread,
Excellent.
zucchini muffin, zucchini cake.
Well, that was getting a little bit closer. So I was actually describing a chocolate cake. You might be thinking, how do you get chocolate cake from flour, sugar, milk, eggs, and zucchini? And this is kind of the list we have as astrobiologists going out looking for life as we don't know it on other planets, based on only what we know about life on Earth. So we have this chocolate cake, and we have this list of ingredients. This is an incomplete list. So characteristics that we can give life on Earth probably aren't all of the characteristics of all of the possible life in the universe. We also have a very specific atypical ingredient. So I like to put zucchini in my chocolate cakes because it keeps them very moist. So how do we know that life on Earth doesn't have a very specific attribute that life anywhere else doesn't have? We're also missing a number of things. We're missing a process, we're missing time, we're missing instructions. And so this is kind of what we're tasked with as astrobiologists. We have a terrestrial bias. We have a data point of 1 when it comes to life. And so if we're looking for what's known as the second genesis of life, or life 2.0, as Dr. Chris McKay would like to say, this implies that life would be common in the universe. And looking for life as we don't know it requires identifying traits that are universal to life, or agnostic biosignatures. And so if we don't really know if life on Earth has characteristics that apply to life elsewhere, and we don't know if life elsewhere might have some characteristic that we've never seen here on Earth, how do we actually come up with these agnostic biosignatures? So there are 3 main characteristics that are thought to be universal for all life: a certain level of complexity, a certain level of selectivity, and a distribution that's not equal, that's not homogeneous. And so as an example here, all life on Earth contains proteins. All proteins are made from amino acids. There are thousands and thousands and thousands of possible amino acids. Life on Earth only uses 21 of these amino acids. So life elsewhere might not use the same 21, but this idea of using a subset of complex molecules, this selectivity and complexity, is thought to be a universal trait of life. And complexity comes in here as well, and I'll go into complexity a little bit more. But 3 of these amino acids, tryptophan, tyrosine, and phenylalanine, are particularly complex. They take a lot of energy to make. And it's actually very difficult to make these without biosynthetic pathways. So the probability that a collection of these amino acids and these amino acids alone in a heterogeneous distribution occurred there by chance is very low. So biosignatures actually play with this idea of probability. What is the likelihood that we could get this observation purely by chance versus how likely is it that we need some sort of life process to be able to build up this observation that we see? Now, is the term agnostic biosignature an oxymoron in itself? I mean, maybe our concept of life is so intrinsic to life as we know it. Maybe we need a different concept, different word other than life or bio or biology to describe life as we don't know it. So this kind of presents these 2 different scenarios. Is life as we know it kind of separate from unfamiliar life? You know, we have this terrestrial bias and it's so intrinsic to our concept of life. Or is life as we know it just this very, very small part of all potential unfamiliar life? And so this is more of a philosophical question that doesn't really have a specific answer. So I'm going to talk about some of the research that I've done now to try to address some of these questions and looking for biosignatures using some of the instrumentation and the technology that's currently on the Perseverance rover. So I'm actually going to turn off my speakers for this one. I went about 5,000 feet underground to a deep mine, the Sanford Underground Research Facility. It's the former Home State Gold Mine in South Dakota, to look for life in the deep subsurface. And how do we find it? And so here we are in the minecart. We go behind these air doors, and so I'm working in an environment that's very hot, very humid, and it's a difficult environment to work in, but it's a lot of fun. So here we have a room for rent. We're very lucky on one of our levels. We actually do have a chemical toilet. So this is the lap of luxury in the deep subsurface. And here we are installing these culture systems in the deep subsurface, part of a NASA astrobiology project. And the image there on the right has all of these tubes and cylinders with crushed rock inside of them. And so I let this underground water, this underground fluid kind of incubate through that crushed rock for about 3 months, come back, pick it up, and look at it. Can I see life? And this is one of the things that we see. So this is a biomass visualization of microbes that actually grew on those rock chips deep underground. So on the right-hand side, you can see all those little round oblong bumps. Those are all microorganisms. So that's a scanning electron micrograph of those microbes physically attached to the rock. And then on the left, we have a zoomed out image. And so this area is about a centimeter. And all of that green is actually the fluorescence of that amino acid tryptophan. And so what we're actually showing here is that patchy heterogeneous distribution of that very complex biomolecule tryptophan that's associated with the microbes that are growing on the rock. And the technology that I use to actually visualize this and look at the fluorescence of tryptophan is known as deep UV spectroscopy. And so, as many of you all know, spectroscopy is basically light goes in and light comes out. And the light that goes in can interact with a target. And when it interacts with a target, it's going to change the light that comes out in some way. One of the ways that light can be changed is called the Raman shift. And so what that is that the target is going to absorb a little bit of energy. And so the light that comes out is going to be shifted in energy a little bit compared to the light that goes in. And that energy shift is very specific to the molecule that it interacts with. And so we can use this Raman shift to actually fingerprint molecules that a deep UV Raman instrument can look at. And so this technology, this instrument is actually currently on Mars. This is the Sherlock instrument on the Perseverance rover. So here's the Perseverance rover in one of the clean labs at JPL just before it was shipped off for launch. And I don't know if you can see my cursor. I can't see my cursor. But if you look at the rover there in the center, on the right-hand side of the rover, there's that gray cylinder kind of pointed directly out at us. That's Sherlock. That's sitting right on the edge of the articulated arm of Perseverance. So Sherlock stands for Scanning Habitable Environments with Raman and Luminescence of Organic and Chemicals, which is really a tortured acronym to saying we're using Raman, so that deep UV spectroscopy technique, to look for organics and other chemicals in potentially habitable environments. And there's just a close-up image there of the Sherlock instrument, and you can see the laser hole where the laser comes out. This is the brass board instrument. So this is Sherlock before the flight instrument was built. So this is the instrument that I worked at JPL, and it's composed of a deep UV Raman laser, an objective and the sample plate, a spectrometer, which is going to split the light, and a detector, a CCD detector, cooled with liquid nitrogen. So what does a deep UV Raman instrument actually see when it looks at a cell? So these are two graphs here. On the left-hand side, you see a breakdown of all of the components of a cell. So if we were to take a cell, you can see it's mostly composed of protein, a little bit of RNA, a little bit of DNA, a bunch of metabolites. So that collection of molecules in those proportions constitutes a cell. On the right-hand side is what a deep UV Raman instrument sees. So deep UV Raman is sensitive to the building blocks of DNA. So that's the cytosine, the adenine, the guanine, the thymine, and the uracil. So these are the DNA bases. And it's also sensitive to those complex amino acids that I talked about a little bit earlier, tryptophan, tyrosine, and phenylalanine. The problem is that none of those molecules by themselves is absolutely indicative of life. All of those molecules have actually been found in carbonaceous chondrites and meteorites. They can all be formed through processes that have nothing to do with life. So when a Raman instrument actually sees these organic signals, how do we know that we're actually looking at a cell versus just looking at these molecules that might not tell us if there was life there at all? So this is a little bit of research that I did with some colleagues at JPL. And so we decided, we thought, okay, these nucleobases of DNA actually occur in different levels of structural or molecular complexity. So you can have just the nucleobase. So if we have just the nucleobase there, that's the base that the Raman instrument is sensitive to. And that's the base that can be formed abiotically, that doesn't necessarily need biology. But if we go up to increasing levels of complexity, all the way up to a nucleotide, so this is the full section of that base incorporated into a DNA molecule, the Raman instrument is still seeing exactly the same bond. It's still sensitive to the same molecule, but the molecular complexity of the environment, the context, going back to our music context, the context of that molecule has changed. So we decided to take the spectrum of a cell. We used E. coli. And so the spectrum of a cell in both of these images is shown in black. And then we said, okay, let's just take the spectrum of all of the Raman active components. And so on the left-hand side, we took all of the Raman active components and used the simplest nucleobase, the smallest part that the Raman instrument was sensitive to. And that's the pink line. And you can see that it's not a very good fit. However, when we increased the molecular complexity, the context of that nucleobase on the right-hand side, suddenly we have a really good fit. So if we have a structural complexity that's actually unique to biological systems, and remember, complexity is thought to be one of these agnostic biosignatures, now developed a threshold for biogenicity, or a threshold to be able to say, okay, is this detection actually likely or probable for life? And so this allowed us to give us a threshold for life detection based on molecular complexity that's unique to biological systems. And so just coming back here, this brings us back to the sense of the whole. We can't use that part of a cell. We can't just use that nucleobase by itself. We need to have it in a complex environment that's representative of an entire living system. So I'd just like to leave with this quote, which was actually published in a very early paper using deep UV Raman spectroscopy. So this was by Nelson in 1992. In a very real sense, the whole is more than the sum of its parts. And I think that sums up very nicely what it means to be alive, and that we really need to think of life as a concept or a system rather than a construct of a bunch of different separate parts and pieces. And we need to keep this in mind, and this idea of context when we start to look for life, signs of life, when we step outside of our concert hall, when we step off the earth. So I just want to acknowledge all of the people that I've worked with. None of this work can be done in isolation. Worked with a number of different institutions over the last 10 years to pull some of this together. Specifically the NASA Astrobiology Institute team, my field teams, and Caltech and JPL. So if we have time for any questions or discussions, I'll ask Dave to stop my screen sharing here because I've lost my cursor control. And thank you very much.
Okay, thank you. That's great. I had a question pop up, but it seemed to have disappeared. And that was somebody was asking, where were those experiments underground? Where were those taken? Was this in the States, wasn't it, someplace?
Yes, so that was done at the Sanford Underground Research Facility, which is the former Homestake gold mine in the Black Hills region of South Dakota. And the closest town there is Lead, South Dakota.
Okay. And I don't recall hearing anything from the Mars mission so far in terms of finding life. Nothing yet, right?
Yeah, no, nothing yet. So what's interesting about the Perseverance mission is it's not actually designed to find life. So Perseverance was really designed to be able to identify samples that are likely to contain signs of life and to collect them and to cache them for eventual sample return. And so Sherlock, as used on the Perseverance rover, is one of the tools that the team can use to actually say, okay, does this sample contain organic molecules? Yes or no? Does this sample contain a collection of organic molecules that's really compelling? Yes or no? And so it allows us to actually stage or prioritize those samples because there's a very limited number of samples that the rover can actually collect. And there's even a more limited number of samples that can be returned to Earth. So it's not a life detection mission or a life detection suite of instruments. It's really a habitability characterization and a sample selection suite of instruments to identify samples that have the highest probability of containing signs of life. And the most recent results of Sherlock were published in the last couple of months. And Sherlock's been successfully able to identify a number of complex organics in some of these samples, which is exciting. No smoking guns. We expect organics to be on Mars, but interesting nonetheless.
Super. So I had comments from the chat box here. One of the fellows said, "Wonderful, lots of parallels to my Deleuzian philosophy." That's what he's into. So I can see some of the comparisons there. And a lot of thank you from everybody for a very interesting presentation. And whoops, hang on, a bunch of questions just popped. What is the oldest accepted MI roof sill on Earth?
Not sure, Tony, what you might be referring to by MI roofs. Are you talking about volcanic sills? Or the
oldest microfossil. Sorry, he just clarified.
Oh,
Sorry.
Perfect. That's an interesting question. So the earliest evidence of life is thought to be isotopic. So life is lazy. It likes light isotopes rather than heavy isotopes. And so there's some very compelling light organic carbon from about 3.8 to 4 billion years ago. The oldest microfossils themselves are a little bit more contentious. There's a whole bunch of papers in the literature between Schaff and Brazier. That tends to be around the 3.5 billion year mark. So I think you'd be safe to say anywhere from about 3.5 to 3.8 billion years. We have pretty compelling evidence for life to have originated before then to be able to build up a signal that we can detect. I'm sorry, I don't have a definite answer for you. That's one of the things in this line of work. We have very few definite answers here.
I'm not sure this is within your ballpark here, but any thoughts on the source of Martian methane? I know on Earth it tends to be more a biological process.
Yeah, actually, that's an interesting question. This is actually one of the projects I'm working on right now, is developing a methane spectrometer to send to Mars. So just backing up a little bit, there are observations of methane in the Martian atmosphere. The first observations were terrestrial, actually, from 1999, and they all tell us different things. So the fact that there's methane in the atmosphere of Mars at all is very interesting. Methane photodissociates, or methane is destroyed in the atmosphere of Mars after about 400 years. And one of the main sources of methane that we thought we knew was from degassing, so volcanoes and that sort of thing. There's no active volcanism on Mars within the last 400 years. In fact, there hasn't been active volcanism on Mars for billions of years. So how do we have recent methane in the atmosphere of Mars today? And we don't know. So there are a number of potential sources and sinks, and there's nothing compelling. So we know that we have a background level of methane that's about 0.4 parts per billion. We know that we have a seasonal cycle of methane. So we know that that methane concentration in the atmosphere actually decreases during the windy season, or the northern fall and winter. And we know they have these methane plumes. And so these methane plumes are the most interesting. And these are these isolated almost massive releases of methane. They're up to about 440 or so parts per billion of methane. So that's several orders of magnitude more methane than exists in the background, and they just disappear too fast to just mix into the atmosphere. And so we know that most of methane on Earth is actually biological, and so methane on Mars is a really tantalizing biosignature. The Curiosity rover has really only made 12 measurements of methane over the past 10 years. And so we don't have enough measurements of methane to really understand these patterns in greater detail. And so one of the things I'm working on is trying to develop the technology where we can do higher cadence measurements and actually describe these patterns in a little bit more detail, as well as looking at the isotopic signatures. So is the methane actually coming from the same source? So could it be from just abiotic water rock reactions in the subsurface? It's kind of seeping up, and maybe every once in a while you get a more catastrophic release of that. Or is this actually a sign of life? We know methane in the subsurface of Earth can both be created and destroyed by microbes. So microbes on Earth can actually use methane both for their carbon source as well as their energy source. So there's lots of research and work to be done here, and nothing definitive on methane sources for the Martian atmosphere.
Okay, thank you. Just a final question here. This is from Joe Holmes. He says, I volunteer for the Canadian Museum of Nature, working with diatoms. Because of their hard protective shell, could they be a candidate for life on other planets?
Yeah, so this is a really interesting question. So diatoms are well preserved here on Earth. The preservation conditions here on Earth allow for their preservations, and they do have this hard shell that can be preserved in the rock record. Diatoms, though, evolved relatively late in the evolutionary history of Earth, and they evolved in response to a very specific environment. They also required very specific elements to be able to make those shells. And so if we have a planet that actually had those environments and those elements that allowed for that accumulation to build those shells, then certainly that could definitely be a candidate. But this goes back to that context idea. And we need to have the right context, not only for being able to preserve the sign of life, but being able to produce that sign of life in the first place. So if we have that environment, yes, definitely, those could most certainly be a great candidate for a biofossil.
Well, thank you very much. That was a wonderful presentation, and we look forward to you coming back. Maybe not so, last time was 2015. Maybe we'll get you back in a couple of years. I'm sure there's going to be some amazing updates from the work that you're doing. So thank you very much again.
Wonderful. Thank you.
Okay, so we're going to move it on to Mark here. Let me, there you go, Mark. Yep. Just check your audio.
Okay, I should be on.
Yes, there you go. So Mark's will be talking to us about polar alignment.
There. Okay, so talk about shifting gears or shifting spectrum here to go from that to this. So I'm going to go through this extremely quickly because at the end there is a link to a much better explanation of what I'm talking about, but it takes about a half an hour to read, and I promise not to take that long to talk about this. So looking at polar alignment, why we do it, why we must do it, how it's done, and a question that doesn't seem to be answered very well in most places I've looked is what precision is required. And then finally, some tools and reference sources. Next slide. So why are we doing this? Well, I truly hope this is not a great revelation to anyone on this chat, but the Earth actually rotates. The Earth moves, it rotates on its axis, it orbits the sun. The sidereal day given there is the length of time it takes the stars to appear to rotate once around the sky back to their original position. So roughly 24 hours, 15 degrees per hour means that the sky appears to be moving at 15 arc seconds per second. And just an aside at the bottom, the mean solar day, of course, is 24 hours. That's what's on your clocks. The sidereal day is slightly shorter than that. And if you work out that difference, there's a 1 day difference in the length of the year. The consequence of that is that the entire celestial sphere appears to rotate once every 365 days for us. Next slide, please. That really didn't answer why, and I'll come back to that. Sky tracking is simply the compensating for that rotation of the sky on a single axis, using some kind of a mechanism to rotate the camera. For that to work, the tracker must be aligned to the Earth's axis of rotation, meaning that it must point at either the north or the south celestial pole. And I've got pictures there of two different very common and relatively inexpensive sky trackers. The Omegon Mount Mini Track LX is a purely mechanical device. There's a simple clockwork, you wind it up and it moves. It's good for about an hour. On the right-hand side is the Skywatcher Star Adventure. It's powered by 4 AA batteries. Next slide, please. So we're back to what is the celestial pole. If you extend true north into the celestial sphere is the imaginary sphere that encircles the Earth, to which the stars are attached, depending on your mythology. The North Celestial Pole is very near to the Alpha star in Ursa Minor, or the Little Dipper being the very end of the handle. And as a consequence, it's often called the North Star or Polaris. In truth, however, Polaris is not exactly coincident with the North Celestial Pole. A close observation will show you, or will reveal, that Polaris itself rotates around the pole in a circle about 1 degree in 1 full degree in diameter, which is about twice the size of the full moon. The original mini track, the mechanical device I showed you, is simply pointed at Polaris, so it's not very precise. And then there's an aside there, for which Mick is not here, so I guess he won't get that. Sorry. Next slide. So polar alignment is the process of aligning the star tracker, whatever form you have, to the pole. As I mentioned, the polar alignment, the mini track uses a small hollow tube. Once we get rid of the slides and just go back to faces, I'll hold it up and show it to you, but it's slightly larger than a ballpoint pen. A newer mini track and the Star Adventure use something called a polar scope. And the idea is the polar scope corrects for the fact that Polaris is not actually at the North Celestial Pole. Next slide. And of course, like everything, there is an app for that. The first shout out goes to something called Polar Scope Align Pro, or PS Align Pro. You can see here there are 3 of the screenshots. Interesting, the shot that's on the right-hand side, simply placing this on your mount, it uses the phone's compass and so on. to actually sort out to give you a rough alignment. That can be done during daytime. You'll see the center one come up again in the next slide. Next slide, please. So this is, on the left-hand side, is the actual reticle that's inside the Star Adventurer 2I. And on the right-hand side is what the PS Align Pro app will produce. The important part here is you'll notice that that both of them have basically a clock face, 0 at the top, running 369 around clockwise. And on the right-hand side, you can see that there's a bright X just after 4 o'clock with the dotted line. This is the PS Align app showing you where Polaris would need to be placed on the reticle for the time of day and place on Earth that you are at. Next slide, please. So this I think is where I'm actually adding something to the argument, and that just how precise do I have to be? And I'm going to attack this from a little bit of a funny direction. Another app, which is which a lot of people will swear by, is something called Photo Pills. The Photo Pills app, amongst many other things, provides the longest exposure possible for a given camera lens configuration before tracking and polar alignment are necessary. And what I've done is I've shown 2 different examples. On the left, both of these are my cameras, the Sony Alpha 99 and the Alpha 77. On the left, with a 300mm lens, the NPF rule, which is the more precise, tells me that in 0.53 seconds, the sky will have moved enough that it will show in the picture. For a 35mm lens on a crop frame, it's telling me I've got about 3 seconds. Next slide, please. So here we get the examples. This is the Sony Alpha 99 with a 300mm lens. Arithmetic tells me I've got 3.1 arc seconds per pixel. The motion of the sky is about 5 pixels per second. That is a 30-second exposure. So my star trails are about 150 pixels long. Wow. Next slide, please. So here what I've done is I've taken on the left is the picture you just saw. In the center, I did what I've called rough polar alignment, meaning I pointed the reticle of the Star Adventurer simply at Polaris, simulating the kind of alignment that you get out of using a hollow tube. And on the right, I took the time to get a good polar alignment. And I think you should be able to see the difference even between the center and the right. However, next slide, please. Here I've expanded them a little bit further, and clearly the center with only a rough polar alignment is still showing stars that are not are simply not round. They're not sharp. Next slide, please. So a different example. This is using a crop frame camera with a 35 millimeter lens, and to a simple eye at this exposure here, or at this resolution on the screen, they all look pretty much the same. However, if you move to the next slide, here you can see that there actually is still a difference. With no tracking, even with a rough polar alignment, this one surprised me because I thought it would have been better, and then good polar alignment. So next slide. So there are other factors that need to be that you need to consider. The tripod has to be level. The tripod has to be sturdy. Using anything, any way of taking these long exposures without having to touch the camera. The biggest one, for me, one of the biggest things was taking the time to recheck the polar alignment anytime the camera is touched. For a long time, I forgot to do things like that, and the quality of the pictures showed. And perhaps again, something that should be obvious, a right-angled eyepiece, such as shown here, gets you away from having to squat down to peer up at that 45-degree angle to align the start. It makes the alignment a whole lot more comfortable. So I think the next is the last slide. So if you want a much better explanation of what I've just talked about, I offer the website at the top. It explains all of this in much better detail, but it doesn't have those great examples I showed you. And then you have the PS Align Pro photo pills and websites for the two mounts and the angled eyepiece. And that should be about the end of it.
A couple of questions. Does the right angle finder revert the image left to right?
No. It doesn't do it. No.
Okay.
I think the polar alignment, the polar scope might be.
Okay.
Yes. Go ahead. Sorry.
No. I just was checking to see. There's no further questions.
Mick Wilson. Who's that?
Mick is here. He's hiding in the background. So Mick is saying, why did he have an octans in one of his early slides?
He knows the answer, and he wants to see if I know the answer. Both of these devices will actually work in the Southern Hemisphere, and therefore this is the way to align with the South Celestial Pole. And one of the methods of doing that is using the constellation octans. So it's the rather than simply lining Polaris up with the reticle, you line up octans with the image that's in the reticle, or that's in the view scope.
Okay, good stuff.
How's that, Mick?
Yeah, I think he likes that answer. Okay, so thank you very much, Mark. And let's see where we're at here.
It's time to move the break, and we're now all of us should be under caution. We now have to be careful on our Southern Hemisphere jokes that Mick is watching over behind our backs.
Yes. Okay, so this is lots of attention on Mars with this opposition, but when was New Year's Day on Mars? And what Martian year has just started and why? So you've got 5 minutes to figure that out. We'll come back at 8:40 and resume the meeting. We'll see you then.
Hi, Bobby.
So Rick Wagner, you're going to be up next according to my schedule here. So Chris, if you want to go to the next slide. So the new year is 26th of December 2022. We are in year 37, and the Mars spring equinox was set as the start of year 1, April 11th, 1955 in Earth time. So that's how they've calculated things there. And then let me see, without further ado, Rick Wagner is going to take us through the RASC Robotic Telescope. So let me just spotlight you here, Rick.
Actually, I will turn off my video. I have a slow internet connection, so it works better if I have my video off. And I will share my screen. Figure out which one's the right one. There we go. All right. So Mick asked me to come and talk about the science with the RASC Remote Telescope. So I'm going to talk tonight about the tools, if you will. And hopefully next month I'll be back and talk more about the science side of it specifically. So the remote telescope is a telescope that the RASC bought about 2.5 years ago. It's a nice looking scope. This is a picture that Jen from National went down on a tour there and went to see the telescope. It's a 16-inch, 0.4 meter Ritchie-Chrétien RCOS tube assembly on a Paramount ME mount. You can see just peeking up above the telescope on the top left, there's a Canon 6D Astro modified DSLR with a 200 millimeter f2.8 lens, so people can do wide field imaging as well. Here's a view of the telescope in its parked position with some of the other instruments. It's housed in a big building. So what have we got here? The working from the right hand end, there's the camera is an SBIG STX 16803 camera. This is a big guy with 4,096 pixels square. That's 37 millimeters across the side by side, which makes it about 60% bigger than a full frame DSLR. The camera also has a small guider chip offset from the main chip so that it can do auto guiding. Next is a filter wheel, 7-position filter wheel. Unfortunately for the science team, it is chock-a-block full of pretty picture filters, the routine LRGB, and then hydrogen alpha, oxygen 3, and sulfur 2 narrowband filters. I think the next item there is an adaptive optics AOX unit that allows for high-speed guiding, can guide out some of the effects of bad seeing. And then finally, there's a rotator up against the back of the telescope that allows us to rotate the whole imaging system to better frame targets or to find guide stars. We control the telescope with remotely using VNC. We have the SkyX planetarium program that also does mount control and camera control. An automatic focuser is run by FocusMax. We use backyard EOS to control the Canon DSLR. And for the astronomy side of things, the science side of things rather, we use CCD Commander to script observations all night. The pretty picture people tend to use more the CCD autopilot, and I'm just learning how to use it, and probably going to move some of the science imaging over to that as well. So here's a view of the software. You can see just top left of center, there's a Toshiba webcam. It gives us a view of the telescope so we can see that it's parked in its proper position. We can slew it around a bit if we need to look at something to see if everything's in position and so forth. The background is the SkyX, the planetarium. To the bottom right is an IP internet-controlled power bar, so we can turn on and off all the equipment remotely. And then CCD or CCD Commander rather is at the bottom left corner. So this is what CCD Commander looks like. This is the script I'm actually running tonight. You can see it starts off with an intelligent cooler action. So it will actually turn on the camera cooler, cool it down to the proper temperature, wait until it's stabilized, and then move on. It does a set of 15 flat exposures of the twilight sky, waits for the sun to set to nautical twilight, the end of nautical twilight, when the sun's 12 degrees below the horizon. And then it starts doing the observations. So it runs little subroutines, if you will, for GI Cygni, which is a Cepheid, KIC 8462852, which is Boyajian's star, or Tabby's star, which is this star that was discovered by the Kepler satellite, which has these very weird deep and irregular dimmings. The next target is a high amplitude delta Scuti called V3124 Cygni. And so here's an example of how I run each target. I start with a comment that just gives me a break in the log file so I know when it was starting. It slews the target to V3124 Cygni. It takes a short image, plate solves it, and determines if the pointing is accurate enough. And if it's more than 1 arc minute off, it will re-slew to the correct position. And then it starts taking, basically, in this case, just an unlimited number of 50-second luminance exposures of the target. And to turn that off, when the target reaches 4 hours hour angle, which means 4 hours past the meridian, it's going to start going into the trees or behind the building. It stops there and then moves on to the next target. So to summarize, the scope, 0.4 meter, f8.9, 3550 millimeter focal length on a Paramount ME. The camera, 36 by 36 arc minute field of view at just over a half arc second per pixel. Gain and read noise for those who are really into the numbers. And the accessories, the adaptive optics, the filter wheel, and the rotator. So here's the view, an indication of the view of the camera. This is in the Stellarium, which I've set up for my own use. And the large red square in the center is the field of view of the main camera. So you can see we can get all of almost all of M33 in. The little rectangle to the left of that is the guide chip. And by rotating the whole system around, that guide chip can be put anywhere in the inside those circles. So you just rotate the system around until there's a nice guide star. In this case, there happens to be one convenient right there. So where's the telescope located? Well, it's at remote observatories, which is just sort of northeast of Fresno, California, up in the Sierra Nevada mountains. Here's a view of the site. Now, this view was actually taken a few years ago, and it doesn't look much like this anymore. I'll tell you why later. So you can see 4 main buildings that each house a dozen or so scopes. And then the other 7 smaller ones in the foreground are private observatories for individuals. Here's a view of the first 2 buildings that were installed. We're in the right-hand building, back left corner. And you can see that at the site, they do get snow, which I find terribly frustrating when I want to go skiing. And California has snow, and we don't. So, location. This is presumably some benefits to being at a site like this. Here's the clear outside forecast for my observatory for 1 week last summer. In case it isn't obvious, the red blocks and orange blocks are basically times when observing is ill-advised cloud and so forth. So the patches of green are when I could be out observing. Here's the forecast for Sierra remote observatories for the same week. I can't imagine what I would do with a solid week of 24 hours a day, clear skies. Another thing they have at the site is they have seeing monitors. They also have sky cameras, so you can check the cloud conditions. The seeing monitors track the seeing, obviously, and you can see here's a night of the seeing ranging around 1 arc second. It's generally better than 2 arc seconds, and I think about 1 arc second is about the best it gets.
Rick, we have a question here. What tool or site are you using for the astronomy weather forecasts?
The earlier ones there it's called Clear Outside. So in my books, a 16-inch telescope is a pretty big telescope. In Sierra remote observatories, it's decidedly subpar. Here's a 20-inch. It's in the same building as we are. A 17, I think, another 18, a 0.7 meter. There's a lot of big optics in this place. You know you've got a big telescope when you have to have a $10,000 or $1,000 an hour crane come in to lift it onto the mount. I was quite interested to see the mounts. You can see them in these 2 pictures. There's 2 of them. These are the new Planewave L series mounts, basically single arm forks that range from $11,500 to $33,500. direct drive motors. They seem to be the thing now. There's a couple of dozen of them at SRO now. So the site, SQM readings generally down around 21st magnitude during the dark of the moon. The altitude is 1,400 meters, which helps explain the snow occasionally. And just a few months ago, they installed a fiber internet connection. So now at the end of a night's observing, I can upload about 700 megabytes of images to Google Drive in about 20 seconds, and then spend about an hour downloading it to my house. So the site is not perfect. It does have some issues. You can see here, this is from 2 summers ago when they had that really bad year of fires, and the fires approached to within well under a kilometer of the observatory, burned all the trees down. You can see the whole place was shut down, enveloped in smoke. This is what the sky looked like at the time. There was ash all over the place. The only good thing about the whole business was that nothing was damaged, and basically all the fuel within kilometers of the site now gone. So we expect that for the next decade or two, the likelihood of fires is very small. So unfortunately, in this world, there's a lot more people interested in doing pretty pictures than there are in doing science. So the pretty picture team gets 4 nights per week of observing. And they have a team that gets together, decides on their targets, how they're going to be imaged and for how long and so forth. And then the data is shared out amongst the team members. And each individual can process it as they choose. Last year, Sky News bought a whole bunch of the data and released it to the public for sort of a competition to see who could do the best processing. And I think every quarter or something, National releases some data for people to play with. So this is the Lagoon Nebula by Stuart Hagee. The center of M33 by Guy Spence. You can see he's used the hydrogen alpha filter to really pull out the HA regions. This is M77 by Dan Meek. This is a very interesting little galaxy that I showed images of a few years ago. It's especially neat because visually under poor skies, what you see is only the very small core. As the skies get better, and your scope gets bigger, you see the larger core, and then under excellent conditions with a large telescope, you see the whole field of the view. Dan Meek processed that one. And then, of course, there are also hydrogen, the narrow band images. This is the Hubble palette of the elephant trunk in IC 1396, done by Jeff Dutton. And this is the kind of images I take. So, sort of a teaser for next month. I hope next month I'll be back to talk about the science. So you can look at this marvelously attractive image, at least attractive to the scientific mind, and anticipate what I'm going to talk about next month. And I'm prepared to take questions if people have them.
Okay, there was just one in the chat there. I think we covered that off.
No, actually, Dave, there's several in the chat. The first one from Andre Paquette. He said he thought he saw a flat panel near the telescope. Why are sky flats used instead of panel flats?
A lot of the telescopes do have the electroluminescent panels set up so they can do that. We do not have one. So we're stuck doing the Twilight Flats. It's one of the Pretty Picture team, of course, is most interested in getting a panel like that. So I suspect when money becomes available, that'll be one of the earliest purchases for the telescope.
Another question, what does it take to fit the filter wheel differently?
To fit the filter wheel differently.
I think they're asking, what does it take to change the filters to something that you might want to use instead of Pretty Picture people?
Oh, well, that would involve dismantling the whole imaging train, taking the cover off the filter wheel and changing filters. The staff down there would be able to do it. So if we were to commit the telescope, say for, a few months or something, strictly to science photometry, we would, we might consider doing something like that. But given that, the science team gets 2 nights each week, Mondays and Fridays, outreach does Wednesday evenings. That's being run now by Samantha Jewett at National. She's doing generally exoplanets with high school students. So it means that, I'm only using the telescope one night at a time when we would want photometric filters. There's been some discussion about the idea of getting an even larger one. I think SBIG was thinking about, or maybe has, or is going to come out with like a 15 wheel filter wheel, but that will be significantly expensive. And I don't expect a great deal of money to be coming towards this telescope in the near future. So.
And just to throw in another question from me, an obvious one for the membership, how would a typical RASC member become involved in this if they were interested?
Well, I'm not going to tell you that till next month. But
perfect answer.
We're working on that right now. And we expect to stand the team up probably in the next few months. And I'm just writing a variable stars course that we're going to give through National, and probably sort of April timeframe. And I hope by then we'll have the whole administrative procedure worked out. And, my goal is basically, if you want to be on the science team, then you send us a note saying you'd like to be on the team, and you'll be able to contribute to the activities.
Okay, thank you very much, Rick. So
thank you.
Okay, so observation reports. Here we go. You're up, Andre.
Hey there, can you hear me?
Yep, no problems.
Great, thanks. So my name is Andre Paquette, and this is an image of M33 that I took across 7 nights in October and November of this year. I am a bit half of what Rick would call a pretty picture imager and half of a science imager. So I do a lot of pretty picture imaging, but I also do some science work as well, mostly in asteroids, not in photometry. M33 is a spiral galaxy in our local group, and it's about 3.2 million light years away. It's smaller than the Andromeda galaxy, and it's also smaller than our Milky Way. I have property out near Fred Lossing Observatory in Benny's Corners, and I have a dome there that I operate remotely from my home in Carp. The gear used in this image includes a 12.5-inch plane wave CDK telescope, an Apogee U16M camera, which is the same, includes the same chip that Rick just showed out in Sierra remote observatories, on a Celestron CGE Pro mount. This image is composed of 49 20-minute exposures. The field of view produced is about 50 by 50 arc minutes, which is just under a squared degree. And so I can take images of fairly large objects with a lot of detail. Could you change the slide, please? So as an example of that detail, here's a zoom in of the top left region of the image showing NGC 604, the core of the galaxy, and a few other icy objects. There's a fair bit of detail here, especially in the H2 regions like NGC 604 in the upper left. One way that we learn about our own galaxies is to study other galaxies, and we can get a good detail from our closest neighbors like M33. Change slides again. Here, I've annotated the image to show a few globular clusters known to be local to M33. There's just enough resolution with this equipment that you can distinguish some of them from foreground stars because they're a little fatter than the expected point spread function from a star. Change slides again. And finally, I'd like to share some fun that I often have during image processing. This is an animation of some of the frames from one of the nights showing two asteroids crossing the face of the galaxy. The one on the left, moving right to left, is asteroid 24866, magnitude 17.1. And the one on the right, which is a fair bit fainter, is asteroid 105743, magnitude 18.2. They're both moving kind of right to left and slightly upwards. Both are main belt asteroids. It's fairly common to encounter asteroids moving across the field by imaging, especially at the declination of M33. And 15 years ago, I was imaging M33 with the same camera, but with a 20-inch telescope. And I saw several asteroids in that imaging session. And that find jump-started my interest in asteroid observation and discovery. And that's all for my M33 image.
Okay, thank you very much. So we're going to turn it over now to Malcolm. You're muted, Malcolm.
There we go. That should work now.
Yep.
All right. Well, thanks very much. I can see from my camera, it's only filming in H alpha by the look of it. I'm a little bit red here, but I'm a new member with the Royal Astronomical Society, and I recently bought a telescope from another member, and he suggested, hey, you should join the club. And so I attended the last meeting and saw that you had people present, and I thought I'd like to show a few things that I've done over the last year or so. I took up astrophotography kind of with a vengeance about 15 months ago. Would have been earlier, but it was about 10 months of wait for my gear to arrive because of all the COVID-related problems in having shipments delivered and things like that. But finally got things up and running. And so I'll show you three different pictures that I think all are quite interesting. The first one here is a section of the moon that I really like. And I saw some conversations on email that seem to be covering, topics related to this area as well. That's Plato that you can see up in the left. And it's pretty good test, I think, for resolution because those little kind of craterlets within it are kind of on the order of 2 kilometers in diameter. So nice test on kind of both seeing and resolution. I processed this image, by the way, with a new program, new to me anyways, called AstroSurface. I think a lot of planetary and lunar people are familiar with AutoStacker and Registax, and AstroSurface kind of does what both of those do in a single package, plus some of the things that you might do as well in Photoshop. So it's kind of a one-stop shop for this kind of photography. Things that I like in this are, you can see the Alpine Valley that bisects the two mares there. One is Mare Imbrium on the bottom, which is the Sea of Rains, and then Mare Frigoris, I think is how it's pronounced, the Sea of Cold. So that valley kind of bisects them. And if you really squint your eyes carefully, you might be able to actually see there's a little rill in there as well that you can sometimes see. I'm not sure I actually have captured it here. Other things of interest, you can see the Cassini crater, which is that kind of round, flat crater, somewhat in the middle there that has two craters inside it. That's a very old crater that is actually filled with lava, basically to the same extent that the rest of the sea is. So that, indicates that the crater is quite a bit older and then was filled. And you can just make outside of the sort of the two dimples of its mountains in the middle there, and then Cassini A and B inside it. Over to the left of that is the Pythons, and you can see the two little craters. And I think my favorite feature is just below that, which is I think it's called Python Gamma or Gamma Python, which is that very small looking, looks like Thor's hammer. And that again, yeah, right there. And that again is the top of a mountain that's basically subsequently been covered in the lava fill from the mare. So lots going on in this area. Fascinating, part of the moon. And I took this on, I think, the last day that we had a clear sky, sometime around December 10th or 13th, right after the Mars occultation. Okay, can we go on to the next?
Sorry, I have to interject, Malcolm, and say that I'm displaying your image on my computer on a 27-inch screen, and the rill in the valley is very clear. You really captured it.
Okay, excellent. This is kind of a fun one. This was taken almost a year ago to the day. It was 2 or 3 weeks after the launch of the James Webb Space Telescope. And they had just opened up the sun shield. And I thought, with the sun shield open, it's probably going to be reflective. I wonder if I can find it. So I found the rough coordinates, aimed my scope, and started taking 30-second exposures. And that's the James Webb that you can see moving across the screen. It was at this time heading towards its L2 orbital location. This is about 45 minutes of travel. So I took 90 30-second exposures and then kind of merged them into a GIF image. And I was just kind of thrilled that I actually found it. It was this is very much a crop of a much bigger image, and as still images, trying to figure out what might be James Webb was pretty tough. I blinked the images until I found something that I thought might be moving, and then I kind of zoomed in on it. Okay, next one, please. Our last image.
That was your last image?
Oh, did I miss one? Was there 3?
Yes, you've covered 3.
Oh, okay, because the first one I don't think I spoke to then, and that was this image. Sorry, I went offline a little bit when I was speaking there. This is the Crescent Nebula and the Soap Bubble Nebula, and this is the image that I just learned tonight because you told me had been selected by Sky News, so I wasn't aware of that. I thought perhaps if you're selected for an image of the week, they would notify you, but they didn't, so I'm kind of thrilled to hear that. The thing that I really kind of liked about it is the Crescent Nebula obviously is, very impressive, but the soap bubble, the fact that it was discovered very recently, 2008, by an amateur astronomer, I think gives us all hope. So that's all for me. Thanks very much.
Okay, thank you very much, Malcolm. So Jim, Sophia, let me just replace the spotlight. There you go.
Okay, thank you. So on December 8th, day of Mars opposition, it was a clear night with good seeing, which is a rarity around these parts. So I had to, I took the opportunity to take a sequence of video images from about 8:40 p.m. to 2:40 a.m., which visually details the surface rotation of the planet. The videos were stacked and processed using AstroTrivia. I used a Celestron 8-inch Smith-Cassegrain telescope, a TeleVue 2X PowerMate, and the Beta UV IR cut filter. The camera was the Malincam Skyraider DS10C Tech model. Mars is really a lot of fun to look at. The surface features are always changing. It was a late night, but definitely worth it. Next one, please. And this is my best shot of Mars taken thus far with the same equipment. Post-processing using Topaz Studio 2 brought out some additional surface detail. Next one, please. And this is a composite image of the solar disk detailing prominence activity as well as surface detail. Now for this image, I used the Lund 60mm H-alpha solar scope, a 1.5 Barlow lens, and the Mellencamp Skyraider camera. When I view the stun, I typically initially look at the complete disk and search for noticeable solar flares and prominences on the periphery. You may notice one at the top left of this image. Next one, please. Then I zoom in and take a video of the prominence and the surface area separately, adjusting the gain of the camera on the fly. And then I stack each and create a composite image that you're seeing now. Thank you.
Okay, thank you, Jim. Richard, you're up next. Hang on a second here while I spotlight you. There you go.
Okay, thank you. Before I talk about my observations, I just have one little bit of treasurer business. I've been trying to get in touch with Karen Finstad. So Karen, if you're in the audience tonight, could you please send me an email at treasurer@ottawa.rasc.ca. Thank you. Okay, this is the beginner challenge for the month. This is M2, a globular cluster. And from my backyard, it was already sort of hiding in the trees. But because the trees were bare, I did manage to find it and take a few pictures, but it was really, I had to throw away most of them because of tree branches across. So this is just a stack of 7 frames. But it is a very nice, bright globular cluster, so it was pretty easy to produce a good image of it. And it's interesting to see the number of reddish colored stars. So I guess that's an indication that it's fairly old stars in this cluster. Next one. Now the intermediate challenge object was something new to me. I hadn't heard of this object before this month, but this is NGC 1333, also known as the Embryo Nebula. And it was very nicely placed at this time of year, fairly high in the sky, but it was a real challenge to see through the light pollution of Ottawa. So, Andrea, there's certainly an example here of the difficulty of observing nebulas from Ottawa in the glow of the sky. So this is a stack of 122 30-second light frames. And then if you compare it to the next picture, this is exactly the same object, and I've rotated it to match up. This is how it looked from FLO. So there's quite a difference with the light pollution from Ottawa and the light pollution out near Almont. And I certainly recommend members of the RASC Ottawa Centre to take advantage of this membership benefit. Go out to FLO to take your nebula pictures. So this is a stack of only 69 light frames. So I didn't brighten up the stars quite as much, but the nebula, and especially the dark lanes across it, showed up so much better from the dark sky. Another interesting thing here is that you get quite a contrast in colors. The nebula around that very bright star is definitely bluish colored, whereas the one to the left of it is a more sort of an orangey red color. So it's quite a beautiful little nebula. Next one. Well, then the clouds moved in, so I didn't get any of the other challenge objects, but I did take a few pictures of Mars. And once again, this shows sort of a difference between 2 different ways of observing. The picture on the far left, I took using the 14-inch Meade telescope in the Paul Commission Observatory at FLO. I get a nice big image with a longer focal length there, but there wasn't a great deal of detail. The seeing was not great. I had some problems pointing high enough overhead. The dome actually obstructed some of the view at times. So a few nights later, on the December 18th, the first one was December 12th, and then December 18th, I just went out in my backyard in Ottawa using my 8-inch telescope with a 2000 millimeter focal length. Smaller image, but quite a lot more detail. And the image on the right here is a tool that I really strongly recommend. Sky and Telescope magazine has a variety of different little apps on its website. This is the Mars Profiler, and it will show you what is on Mars at a particular time and date. So you can use this to identify the features that are on your pictures you take yourself. So definitely on my second picture, you can see this Mare Acidalium at the top, and even the separation between Mare Serenum and Solus Lacus down in the south. So I was quite interested to see that level of detail, but you know, sadly, on the day I was out at FLO, it was rotated a little bit to the left. So there's a big blank area on Mars, and Amazonas and Tharsis, where there aren't really very many features to be seen. So all of these factors go into what you can see on Mars. The telescope, the focal length, the height, the altitude of the object, the seeing of that particular night, and also simply what's pointing towards the Earth. And can make a difference. Okay, that's all for me. Thank you very much.
Okay, thank you, Richard. Taras, you are up next.
Thank you, and sorry, I have to apologize for my coarse voice. I'm overcoming cold, and yeah, I still hope you can hear me well. If not, let me know. So this was supposed to be a rare astronomical event happening December 7, 2022, between 10:30, 11:30 p.m. as seen from our location, an occultation of Mars by the moon. That night, Mars would be seen in close proximity to the moon, eventually hiding behind its disk or ingressing, and then reappearing on the other side, egressing some 50 minutes later, again, as if it were seen from our location. And the planet would be at its best one day before the position, 17 arcseconds diameter in all of its beauty. There was nothing much needed to observe it, except for location, 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 as Rick mentioned. So just the clear skies were needed. And yeah, right. So what you can see in the picture is the coverage, cloud coverage. It was a forecast one day ahead of the event. And as you can see, the whole northeastern Ontario would be covered with a thick layer of clouds. So there would be a still large area of open skies in northwestern part of the province to the west of Wawa, or with an even larger certainty around Thunder Bay. And I did take a couple of days off from work. I hoped that I can make it to some distant place like that. So I thought that it would be worth taking the ride. And as long as clear night is provided. The choice was limited, so, and again, I cannot go much farther south, because when you move south, this occultation path would be such that the Mars would never hide behind the moon. So my only option was going west. And the only way of going west with this area in yellow that I circled with the town of Marathon in the center of it. And I thought, well, let's see what it will take for us to get there. And let's go to the next slide. And it would take 13 hours of nonstop driving to get under good driving condition to get there. But reality wasn't too good. There was Highway 17 closure on quite a long span. And to get to Marathon, I would have to go all the way around, taking a northern route. And that would add 2 more hours to the trip. So besides, there was still not much of certainty whether this area will be with a completely open sky, because you saw there was a still patch of thin clouds above the Great Lakes. And I was wondering whether it was worth taking the chance or not. Let's go to the next slide. So in the morning of December 7th, the forecast changed a little bit. And you could see that there were kind of like a sucker hole in the area south of Hamilton. And particularly the center of that yellow circle is the town of Caledonia. And I thought that's where I should go to, and it took me 6 hours to get there. Let's go to the next slide. So when I got to the spot, yeah, there was no need to guess twice. There was a sober overcast. I guess I must have looked silly to local people trying to set up my telescope and start adventure in the middle of parking lot near Home Depot under bright light and an overcast sky. So let's go to next one. It was not until 10:49 when the cloud layer became thinner, just thin enough for the moon to show up. Actually, can I go slide back, please? Yeah, so this was a comment for this picture about the first shot which I took at 10:49. And yes, it is occultation of Mars by the moon. And where is Mars, you ask? Well, it's occulted by the moon. It's behind it. So there was not much to see. And I was a little bit disappointed. And moreover, very short after I took this picture, the clouds moved in, and even this view of the moon through the skies was gone. Let's go to the next slide. So it was not until 11:17 when the bleak shape of the moon showed up through the clouds again, and I was able to snatch this picture with the Mars already egressing and continuing its journey away from the moon. You can see that little tiny dot is actually Mars, as close as I could have gotten it right during this occultation when it was leaving the disk. Let's go to the next slide. I thought it might be it, and the two pictures are better than none. But then I kept waiting until clouds started to thin out again, and this time after midnight, around 12:40 or so, while the planet traveled quite away from the moon on a distance comparable to the diameter of the moon. You can see it as a really tiny spot to like 4 o'clock in the direction that equals the distance. Yes, that's the one, the distance of the diameter of the moon. So that was my second chance, and it was still occultation, but a little bit kind of further not than it was supposed to be. Let's go to the next one. Yeah, I managed to take a few more shots, and this is actually one of those with a little bit better quality when the clouds got a bit thinner. So you can see that later on, after 12 o'clock, closer to 1 o'clock, the visibility was improving. And let's go to the next slide. And this is actually what the planet looked like through the skies, through the clouds rather. And you see how much of a difference there is in the brightness and in the shape and in the details, depending on the thickness of the clouds passing between me and the planet. Luckily, I was able to take a few more videos like this and then stack them. And let's go to the next slide. Yeah, so this was a stacked version of those previously taken videos with best frames selected. I got some little bit glimpse of some details, and having that, I thought that, well, once I have this, maybe let's try to recreate what this view would be like if I did go to marathon. And I did suspect that it would have been a better destination even if I had driven much longer. So let's go to the next slide. I entered the coordinates and timing into Stellarium and tried to match planet's position by using the data from my pictures. Stellarium screenshot on the right side shows the location with the right arrow pointing in that location. And the timing is when one of my pictures with the moon were taken. So I had the right lunar landscape. I tried to match them to the best of my ability. And let's go to the next slide. And this is what I've got, which is what the occultation would look like as if seen from Marathon, Northwestern Ontario. I guess we missed quite a show with our weather conditions, considering how graciously the planet would look hiding slowly behind the lunar surface and how it was mysteriously reappearing from the other side in real time. This could have been observed within a matter of minutes, especially the motion above the surface. And let's go to the next slide. So next day, December 8th, we were granted a beautiful day with clear skies, better than average seeing conditions. And I was able to take this picture of Mars right from my backyard. This was about 10:25 p.m. I'm glad and partially surprised of the fact that a thin bluish ring of Martian atmosphere did show up in this picture along the planet's limbs, and the surface itself has some details due to good seeing conditions. Thank you.
Okay, thank you, Taras. So what was the telescope that you used in your backyard?
On my 8-inch Schmidt-Cass.
Okay.
Same
Well, that's
as
amazing
for the
image.
other trip. Thank you. But again, it all apparently depends on the conditions.
Of course. Okay, Oscar.
Of course, I've got to intervene first and wish Taras a Merry Christmas and Ukrainian Christmas.
Oh, thank you. Дуже дякую. Вітаю з Різдвом.
Hey everyone. So hope everyone had a good holiday and a happy new year. So I've got two images to show tonight. This one here, I'm sure, is nothing new to anyone. We've all seen this a million times. But this is Messier 27, the Dumbbell Nebula. So it's a planetary nebula in the constellation Vulpecula, about 1,360 light years away, 7.5 magnitude in brightness, and about 8 arc minutes in diameter. So this image was actually sitting in a folder of unprocessed data from about 4 years ago. So this was actually taken July 19th, 2018. 11-inch Celestron Edge HD at f10 using a Canon 60DA DSLR. But overall, I was pretty pleased with the picture. Got some good amount of detail in the nebula. It's 43 300-second sub-exposures for about 3 hours and 35 minutes of total integration. All right, next one, please. So this is the intermediate challenge from last month, NGC 1333, or the Embryo Nebula. It's a reflection nebula in the constellation Pegasus. It sits somewhere between 960 and 1,200 light years away, being part of the Perseus molecular cloud. It's a young and very active region of star formation, and contains several star clusters that are still embedded in the cloud from which they formed. So this whole cloud here is about a mass of approximately 450 solar masses, and it's a pretty cool object I found. As Richard mentioned earlier, the contrast between the blues and the reds, and also the dark, dusty nebulae and the bright areas is a pretty cool dynamic object. So I took this image on the nights of November 27th and December 13th. This in 2022. It was an 8-inch Celestron Edge HD using a ZWO ASI 2600 mm Pro through an LRGB filter set. So each of the colors got about 2 hours of exposure. So 180 seconds of exposure in each of RGB, and about 7 hours and 36 minutes in luminance, or 152 3-minute exposures in luminance, for a total integration of 13 hours and 36 minutes. Yeah, this was it's probably one of my favorite objects that I've imaged so far. But yeah, that's it for me this month.
Okay, thank you, Oscar. So, Paul, let me place the spotlight with you. You can turn off your video if you wish, Paul, or you can leave it on, and I'll let you know if you start breaking up.
Okay, I think I will. Yeah, I'll try to avoid that because, like Rick, my internet connection isn't anything too special. Anyway, so good evening, everybody. Hope everybody had a great holiday, and I'm thinking that a lot of people must have got a lot of Astro gear this winter, because really, honestly, we haven't had a decent sky in like a month. And I won't mention any names, right, Oscar? Oh, sorry, I didn't mean to. Sorry, didn't mean to let the cat out of the bag. But anyway, I hope all of you that did get equipment are able to find a use for it. You know, like paperweights and things like that. And you know, maybe in a month or two we'll get some clear skies. So anyway, that's my gripe. Well, not quite finished griping yet, because I was actually pretty disappointed. I was really looking forward to imaging Mars at its time of opposition, and I see a few members had some lucky breaks with some half decent seeing. This image that you're looking at is basically the best that I managed to get, and honestly, every night that I went out, that it was clear here, because my scope that I was using for this is primarily the 11-inch in my dome, so it's not something I would lug out somewhere in the middle of nowhere to find a clear spot. I was using that and taking some images of Mars while I was trying to do some work on the 14-inch Schmidt-Cassegrain at FLO. So just a collection of shots here. You can see the top row is my stuff there. Honestly, the seeing, even though we did have some clear nights, the seeing was just god awful. It's I was going to show a video there, but I knew we were a bit pressed for time. The seeing was terrible, and these are the best that I could pull out of it. I'm going to try to reprocess this going forward with a bit of a different technique, but anyway, that's for the future. The row down below is a representation from a program I use to do a lot of my telescope pointing and such. That's from Starry Night Pro Plus, and you can see that it shows you this Mars in 3 dimensions, kind of like the Mars profiler that Richard was talking about. But this gives you a 3D representation, and you can see what features are on Mars, and you can see there's a pretty good correlation, even though my Mars images were definitely subpar. I'm hoping to pull out a bit more detail. I noticed when I was putting this together, actually the one on December the 13th, if you look at the sort of the center of my image and then you look straight up, you'll see a round circular bright patch. I don't know if you can point that out. Yeah, right there. That's the one. That's actually Elysium Mons. That's one of the largest volcanoes on Mars. It's not Olympus Mons. That's not visible at this hemisphere right now. But that is the Elysium Mons, a very large feature, and I'm hoping to be able to pull that out a little bit more. But anyway, that's for the future. Bottom line is these images were taken the November 26th and the December 12th images were taken at FLO. while I was doing the work on the 14-inch scope. The other two, December the 10th and the 13th, were taken with my 11-inch at my home observatory. So not the greatest opportunity of Mars, but we have to take what we can get. So I hope those of you that did get a chance to check it out did see something there, because we've got another couple of years now to wait until the next opposition, and it's not going to be as great, I don't think, in terms of elevation. Next one, please, Chris. So Taras, I can really empathize with you, and I got a number of shots very similar to yours. As I said, I was hoping to view this this event with my 11-inch and do some high-res imaging of Mars ingressing and then egressing, but that was not to be. It was like the weather that you described. It was pretty much the same as I had at my place. The ingress was totally overcast. I was keeping an eye to the sky with equipment at hand, but such was not to be the case there. 50 minutes later at egress, again, the clouds were there. It wasn't until about almost an hour afterwards, at 19 minutes after midnight, that I was able to get a shot, and this was just with a 420 millimeter lens. And you can see Mars just down below the moon and to the right a little bit there. Very hazy sky at this point in time, but that was the first image I was able to take after the egress. So missed it by about an hour, unfortunately, and got a lot of nice nifty cloud shots like you did. The next one, please. This one was a little bit clearer. The clouds had thinned out a little bit, and definitely a better definition on the moon, and Mars was a lot more prominent. So I took a pile of shots there. This is one of the better ones that I got there, and you can see Mars is a lot more prominent than the previous one. But again, that was 2 hours after the event, so unfortunately we did miss it. Just as a sidebar too, Taras, after this event, I checked out the satellite images during the time of the event for our whole area in southern Ontario, and it was just abysmal. But there was, and this is nothing you could have predicted, there was one sweet spot that if I was psychic and prescient, I would have gone down there, but it was down just kind of near Perth a little bit south of Perth, where they actually had a sucker hole that formed just at around the time of ingress, and it closed just after egress. So it was actually, it was very close to Westport. But as I said, you had to have been a psychic to know that one. Anyway, maybe next time. All right, next one, please. This is just an image of the moon that I took on the same night that I was doing the Mars work on the 12th. Just again, it was a bit of clearing there, and the moon's a little bit more forgiving than something like Mars because of the large structure there. This is a particularly favorite sort of phase of mine because I love seeing the edge of the Sea of Crisis, Mare Crisium, and the ring of mountains surrounding that very flat plain up near the 12 o'clock position there. Plus a line of really interesting old craters from the southern highlands just dotting the eastern limb of the moon there. So it was a fortuitous shot. All right, next one. And last one. This is one, actually, Rick mentioned this as well with the scope. This is M77, and I've been working on this one for a little while because this is a tricky galaxy. Visually, I mean, I've seen this through a number of different scopes, and visually you can see detail in the innermost core, which is actually quite bright. This image was really processed because that outer ring that you're seeing is a very, very faint compared to the inner portion where you're seeing dust lanes and the central portion of the galaxy. I mean, if I hadn't done the equalization on that and just exposed for the rings itself, I mean, the whole center part would have been totally saturated, totally blown out there. So visually, it's an interesting galaxy, especially through a larger scope there, but certainly with imaging there, you can actually see some of this outer outer detail there. And this is an interesting galaxy because it's a super galaxy, which means it has a very active galactic nucleus there. And some recent work on this has indicated that the part of the activity of this galaxy appears to be the merger of a smaller galaxy, a satellite galaxy, perhaps 2M77, some few billion years ago, which caused an acceleration or a ramping up of the amount of star formation there, and probably fed what is believed to be about a 10 million solar mass supermassive black hole at the center of this galaxy. So a lot of X-ray emission, a lot of radio emission. It is an interesting galaxy, and so this is a combined shot. I had to expose 15-minute subs to pull out a lot of detail on the outer ring there. This is a combined exposure of about 7 hours on this galaxy. So M77, one of the largest of the Messier galaxies, and at its full extent to the edge of the outer rings there, you're looking at about 100,000 light years in diameter. So somewhat smaller than our Milky Way, but a very different kind of structure. All right, that's it for me. Clear skies, hopefully, everybody, and we'll talk to you again soon. Take care.
Okay, thank you very much, Paul. So lastly, here are the challenges from last month, and some of you got those, which is great. So the challenges for this month, the Messier 35, Open Cluster in Gemini. There's the details there. All these will be in Astronotes coming out soon. Next one, the intermediate challenge, NGC 2174, also known as the Monkey Head Nebula. Again, check your Astronotes for the details around these. And for the next challenge, our advanced challenge is IC 2196, an elliptical galaxy in Gemini. And yeah, that'll be a challenge to get to that one. And our lunar challenge is crater Langrenus, and it's an impact crater near the eastern lunar limb. And again, details will be in our Astronotes. The summary of what our challenges are for this month. I think our biggest challenge will be clear skies, though. And our Fred Lawson Observatory is open, and members are encouraged to, use this facility. Our next member-only star party is January the 21st. There's a new moon, and hopefully we'll have clear skies then as well. So here are some of the folks that run our club. Our flow director is Rick Scholes. Stanmont Book Library, which is currently closed, but we do have some books out of there, is Estelle. The Ted Bean Equipment Loan Library. Darren is moving away from this position, and we're currently filling this position, and hopefully we'll have some details for you shortly on that. Coffee and Conversation, that position is open. That is somebody who's going to be at the museum after the meeting. I'm hoping we're going to get back there soon as well. Art Fraser looks after the membership and the membership cards. So thank you, Art, for that. Tonight, we had roughly 80 people. Thank you to all the organizers and the speakers. A special thanks to Haley Sapers for her marvelous presentation, and to all the other folks who did their presentations as well. Special thanks to the RASC National Office, who allows us to use their Zoom facilities. Comments and ideas, Mick would love to hear them. Please send them to meetingchair@ottawa.rasc.ca. Next meeting is Friday, February the 3rd, 7:30 p.m. Same bat channel. So we'll see you folks then.